All right. Hello, Code Camp Cluj. It's so awesome to be here again. I, like James, for some reason, keep getting invited back. I don't know why. I guess we do something right. What Florian was saying was actually kind of funny. I had to chuckle because in London, Neil and I were teaching two different classes, 2 3-day classes. One was on the fundamentals of software architecture that I was teaching. Next door, Neil was teaching a 3-day architecture, the hard parts, both based on our books. Well, at lunch, or I think it was the break, we said, let's swap. Because it's both of our materials, and I could pick up exactly where Neil left off, and he could pick up where I left off, and so we did. And it was really interesting seeing the reaction. I looked up at the slide that Neil was doing after the break, and I came in and I said, okay, everybody, let's get started. So now, when we talk about a saga, and people were like, you're in the wrong room. It was a lot of fun. But we won't do that on this session, because this is all new material. What I want to talk to you about is something I'm really, really passionate about. And that's not only architecture, but making architecture actually work. Let's listen to a conversation here. We have a product owner, a business sponsor, and that business sponsor says, look, I need an architecture that can support 500,000 concurrent users with an average response time of 600 milliseconds under load. And of course, what does the architect say? No problem, I'm on it. And so that architect creates an architecture that in fact will support 500,000 concurrent users at an average response time of 600 milliseconds. So the architect meets with the developers and says basically, here's my architecture, and explains it. What do you suppose the first thing happens? The developers have questions. So we have a question. Our first query is, well, what sort of protocol should we use in between the services? And what do you suppose the architect says? Come on, you all know it. It depends. No. For once, that's not the answer I was looking for. It's the other thing an architect always says. Oh, that's an implementation detail. How often have you heard this? Or the architect or the development team says, well, what sort of persistence framework should we use? What do you suppose the architect says? Again, an implementation detail. Look, I'm in charge of the architecture. You're in charge of implementation. Now go do it. And of course, they do. So after the production release, we have our system, and the very first thing that happens is that wonderful 403 or 408. Then we keep using the system, and then the wonderful 503 happens. And basically, the whole system comes crumbling down, including the projector. No, that's on purpose. Why does this keep happening? It has a lot to do with the fact that implementation does, in fact, matter. It is not just an implementation detail, but the architecture must be aligned with that implementation. And that's exactly what I'm going to show you in this session. The first thing I'm going to show you in part one is really that intersection between architecture and implementation. Where do they meet? How do you see an architecture through your source code, through that implementation? The next thing we're going to see is how they usually diverge and go their own separate ways. And I'm going to show you 3 real, actual examples of where architecture does not meet the implementation. Part 3 of this talk is going to be aligning them back together. I'm going to show you a few tips and techniques to ensure this alignment. So where is this intersection between architecture and implementation? Turns out that intersection occurs with what's called the logical architecture. Let me explain what I mean. Let's take a look at this building right here. We see this floor of a house. And if we really analyze this, we can start to see that it's basically made up of different rooms. We have a couple of bathrooms, there's a bedroom, a kitchen, some more bedrooms, and of course the stairwell that we see here. These rooms all work together to form the structure of that house. Now, we have the constraint, which is the outside dimensions and particular walls that hold the roof up. But outside of that, we can pull these rooms out, move them around, kind of combine them and stuff. These rooms form the building blocks of that house. In the same way that these components form the building blocks of our systems. Whether they happen to be monolithic systems, whether they happen to be services. The point is, the logical architecture, these components form the building blocks of a software system, of an architecture. So let's come back to our question here. Where does this intersection occur? How can we actually view the architecture through our implementation, our source code? This is how. When we look at our source code, we're going to group these particular components by domains. This is all the ticketing stuff, let's say, or ordering. This is all the order processing. When we look at the way we structure our code, now I'm showing a directory structure here. It could be a namespace in C#. It could be a package structure. It could be a directory where our code is located. So the point is, how we structure our code is the architecture of that system. The higher level nodes represent the domains, and then the leaf nodes all represent each of those components. That's when you look at your directory structure, or the namespaces, or the package structures, you are actually seeing your architecture. Let me further this kind of concept. And let's focus on this payment component. It's a building block, a logical component of the architecture. We choose to write some source code. Let's say it's a credit card.java class, so we can charge the credit card. Well, that code has to reside physically somewhere, so it's in that directory. But that directory also represents that component, which translates to the fact that this source code is part of a architecture component. It's part of the payment processing component. That's where they intersect. That's how we see the architecture. Now, what I want to do is show you 3 kinds of alignment to be able to kind of bring the architecture that we design and the source code together. But I'm also going to show you why it doesn't work. I'm going to show you 3 kinds of alignment. The first kind of alignment are operational kinds of characteristics: scalability, availability, fault tolerance, overall reliability. The second is the overall structure of our system. I hope this building doesn't fall down. Why are we all confident that we didn't even think of that until just now? Thanks, Mark. Because we assume this building is structurally sound. Are your systems structurally sound? We'll take a look at that kind of alignment. And third, the other kind of alignment is on constraints within your system. Well, let's start our little journey and put some stop signs on the other roads. And actually, let's take a look at the operational characteristics first, the operational alignment. Let's listen in on another conversation, because the business says this. Well, we're expecting anywhere from, several thousand to upwards to 1 million concurrent customers in this system. All right, what does the architect do? Well, the architect goes to Neil and I's star ratings chart from our Fundamentals of Software Architecture book and does some qualitative analysis to determine what would be the best architecture for this. Well, we know our concerns are elasticity and scalability. Well, we take a look, and sure enough, microservices has 5 stars, the best for each of these. So the architect takes this knowledge and says, compared to the others, given the other trade-offs, I'm going to choose microservices for this project. And it turns out that that was the correct choice, because for that kind of extreme scalability and elasticity, microservices with its bounded contexts provides that because of the fine-grained, single-purpose nature of these services. Good choice, and the correct one, because that will support upwards to 1 million concurrent users. Okay, so the architect has a conversation with the developers. They're all on board. And we have 2 services here. Notice an order placement, to be able to place the order, and an inventory service. But the developers realize that the order placement is actually going to have to make a call over to inventory to get the current inventory counts, and then return those. And what do the developers correctly say? Too slow. It's also coupling these services together. That's not good. So what do they do in response? They do the right thing. They choose to use in-memory replicated caching. Where the inventory has an updatable cache, order placement has a read-only, and they choose to use Hazelcast as a tool to keep these always in sync. That way, when there's an update to a product or a change in the inventory, that change goes into the cache, and it's automatically replicated. Fantastic. Nice. It's much faster, and these services are no longer coupled together. Beautiful. Everybody's doing the right thing until after the release. Because what happens? We start to scale. And we have a 500 megabyte cache. And we continue to scale. And we continue to scale. And you can start to see we're only at several thousand users. And all of a sudden, you can notice what's happening. Crash. Which in turn brings the entire system down. Yeah. What happened? The architect made the right choices for the architecture side of things. Microservices that does support scalability and elasticity. But what happened? The implementation of that architecture was focused on performance and coupling. And this caused a misalignment between the implementation of that architecture and what the architecture was expected to provide. This is a real scenario and also a really good example of that operational kind of alignment. Let's talk now and move the stop sign over and talk about structure. So let's look at a different kind of problem here, structural alignment. So the business says, well, we need a new system for trouble tickets. As customers have problems, they can kind of enter a trouble ticket, and we'll send experts out into the field to your home or workplace to help you solve that problem. Okay, what's the first thing we do? Let's build a logical architecture for it. And this is my architecture. Like this building, it's structurally sound. I analyze the coupling level between all these components, the size of the components, the interactions, all of those kind of considerations. And then we implement it. Structure. This is what the developers came up with for the implementation of that architecture. Looks okay until we match it with all that work we did for architecture. Can we see the structure of our system in this source code? Well, certainly, it looks like email notification goes to customer notification, but close ticket, I don't know what that matches right here. And by the way, completion looks like it matches, but then where is our ticket assignment? It's buried in this structure of the source code, as is things like the customer profile. I don't even know where to go to see that. And do you see what happens? We spend so much time working on architecture, and we don't even see it in the source code. It doesn't exist in that system. Why? Because this is the logical architecture represented by that exact source code. And if we take a look at that structure versus the structure that I came up with, they're entirely different. Another good example of failure. I don't know, there's an architecture to this building right here. Can you imagine if the contractors, the builders said, this is stupid, let's just do our own thing and implement it some way. Does it still have all the load characteristics it needs? What if it starts to snow? Is it going to collapse? That's part of architecture. That's what we do as architects. So what we see on the structural aspect is a misalignment between the architecture and the implementation, the structure of that code. One more alignment that I want to show you, and that happens to be constraints. The constraints, those decisions an architect makes, are they being implemented correctly? I don't know, maybe. Another area for misalignment. Let's take a look. So when we look at constraints, we have a very tight budget and time frame. Okay, none of us have ever heard that before, but let's pretend. And we expect a lot of changes to the underlying data structures, underlying database in this new line of business as we learn more about it. But here's our need, says the business. When those database changes occur, we need those to be fast as possible. Okay, says the architect. So what do? They go back to our star rating chart, and they say, well, our biggest concerns, of course, are cost and time. Let's do microservices. Let's not. But then we also see the way an architecture is partitioned. And so we notice that, it looks like monolithic or even layered architectures are a good fit, but only 1 star for domain partitioning. Now that was an odd one that we had to reconcile, Neil and I, because 1 star is bad, 5 stars is good. So it's bad at being a domain partitioned, which means it's a technically partitioned architecture. And the architect correctly realizes, due to that technical partitioning, I can actually isolate database change in my system. Because each layer of the architecture has separation of concerns with layers of isolation, which means this makes change easy. We know we're going to be changing the database constantly. What do I have to change in the architecture? This layer, none others. In order to make this to work, which it will, I have to put constraints on the system. And what are those constraints? Well, constraint number 1, presentation, business, and services layers cannot talk to the database directly. Constraint number 2, all developers have to respect open and closed layers. A closed layer means that I have to go through that. I can't hop over it. Constraint number 3, all database logic has to go into the persistence layer. There we go. Make it happen, developers. Okay. So we start coding, And the user interface developers realize that it's a whole lot faster and easier just to call the database directly. So they code it that way. The back-end and services developers realize it's really annoying to have my database logic separate from my source code. They want to have it together. It's easier to maintain. So they code or implement that architecture that way. Let's go through production release. And this is what happens. Sure enough, immediately upon release, we have our first database change. That was expected. And guess what I have to change in the architecture? The persistence, the services, the business layer, the presentation layer. Yeah, what do you think about this? Not going to happen. We have failed in that architecture because it takes too long to make database changes. This was the primary concern of the business. So we could see another alignment problem. The architecture absolutely supported that agility, that ability to respond quickly to change with layers of isolation. But what did the implementation focus on? Performance and maintenance. And once again, we see a misalignment, where all of a sudden, we're not supporting that architecture. Do you see in all three of these cases, everyone, it is not an implementation detail. In order to make architecture work at all, it has to be aligned with the implementation. So they're way over here on the roads. Let's spend the rest of this session bringing them back together. And I'll show you a few tips and techniques for ensuring that the implementation matches our architecture. And the first of those techniques is governance. Welcome to the world of architecture fitness functions. Now, I'm only going to talk a couple of minutes about these. Fortunately, you're in luck because Neil's going to spend 45 minutes talking about them. It's awesome. Thank you, Neil. That was very nice of you. An architectural fitness function is like a test. It's some sort of measure, an objective measure of some sort of integrity condition, whether it be scalability, whether it be agility, whether it be structure. Now, a lot of the tools that we use happen to actually be fitness functions, observability, measurements that we can actually track. But sometimes we don't have access to those tools, or they measure, and there's a big screen up there that shows that now we're in trouble. Not much use to us. I use these tools when I can programmatically extract all those wonderful metrics. Sometimes we can't. Sometimes we have metrics, lost messages, that some of these tools do not actually measure. Maybe it's agility, maybe it's structure. And so for those, let me show you an example of a fitness function. So we take any system, service, web app, and we basically stream out some sort of metric. Let's say it's response times over to something like Kafka. Then we write a capture service, which then takes all that raw data, filters it, decides what we want, and captures that raw data and stores it. Now the fun part of the fitness function, and that's writing the actual fitness function itself. That analytics service that now looks at that raw data and starts measuring trends. It looks to see if things are getting worse or things are getting worse, or better or worse, better or worse. And if the trend is starting to get worse, then notify me. This just runs in production. We don't even know it's running. Let me show you an example. So that analytics service or another service can take all that trend analysis and generate these kinds of graphs. So we start to see over time This is just all being tracked, all being measured by all these fitness functions down in production. And do you notice? We're having an increase in user load. But basic mathematics, whether I do slope analysis or variance or standard deviation, shows our slope is pretty close to zero. You know what that does, everybody? It does a couple of things. It demonstrates that we, in fact, are scaling. It also can be used that I can say, what's that slope? What's our variance? The slope is actually moving up. Now I can demonstrate that we are not scaling. It's another really useful tool or thing we can do with this tool. I think this building is structurally sound. It's, I don't know, looks sort of new, but it's probably 10, 20 years old, maybe, I'm guessing. Maybe the apartment building or house that you live in was built many, many, many decades ago. How do you feel about the structure of it? I think it's fine. Do we know? Well, kind of measuring it or something, I guess. These fitness functions can be also used to predict that we're in trouble or when we're going to be in trouble. For example, I'm measuring this, and all of a sudden I see the slope go up. Well, at some point, I can start using mathematical extrapolation to show that curve, based on current conditions, move up and up and up until our failure point, which might be 2 months out. That's, my friends, something I could take to a business stakeholder, an owner, and say, in 2 months, this system seems like it's fine, doesn't it? Oh yeah, our systems are running great. In 2 months, they won't be. That's the time to attack that problem, not when the system suddenly fails and everything's a crisis mode. Oh, it's wonderful tools. But that's good for operational stuff. But what about the structure of the system? Yeah, none of these other layers can access the database directly. Another measurement we can do is a fitness function. Things like ArcUnit for Java, ArcUnit.net for .NET, NetArcTest for .NET, Sonograph for a host of about 6 or 7 different kinds of languages. We could actually code and run as a test our architecture decisions. Here it is right here. Presentation layer cannot talk to persistence layer. Classes that reside in a package presentation should. No classes, there's 2 ways to write this. No classes that reside in a package presentation should access classes that reside in a package persistence. Check. That's pretty cool. It allows an architect to actually code. Here's the same thing in C# using NetArcTest. These are fitness functions, everyone. These are tests that we can actually run in production. What about the structure of our code? I could write fitness functions to do that as well. Classes should reside in a package, ticket, or customer, or survey, period. These help force all of those directory structures, all of our package structures, our namespaces, to be aligned with my architectural components. Okay. Kind of interesting. One way to actually ensure alignment. However, there's a problem. These tools, these fitness functions, these tests, are good at telling you that you're misaligned, but do nothing to ensure that alignment. This is only half the story, everyone. The other half of the story has to do with communication and collaboration. This is actually how we make it happen. Oh, still use fitness functions, because that's how we know we're not collaborating or communicating enough. They tell us we have a problem, but what we really want to do is to avoid the problem in the first place. So let's do that, because communication and collaboration are two separate things. Let's talk about communication first. Well, the most effective way of solving our problem with this constant database change is closed layers in the traditional n-tiered layered architecture. Cool, the monolith's not dead, everyone. Still alive and well. But how do I communicate this to my development team? Dum-da-da-dum. Architecture decision records to the rescue. ADRs. Yes, these days, a talk mentioning ADRs, or architecture decision records, are the same kind of talks that we go to conferences that talk about Conway's Law. Neil and I actually joke about a architect's game or a conference game. Any session you go to where somebody says Conway's Law, you have to take a drink. Everybody would be walking around stumbling, totally drunk. Well, it's the same thing now with ADRs. But ADRs to the rescue for both communication and collaboration. So an architecture decision record is a short text file, 1 to 2 pages long, that describes one single architecture decision. And there's 5 main sections: the title, the status, whether it's proposed, accepted, or superseded, the context. We write a paragraph or a couple of sentences describing our problem. And then the alternatives. The best part, the decision, which is the why. And also, finally, the consequences section. This is where we document our trade-off analysis and impacts based on the decision I made. So, here's a couple of rules that I'm going to show you. If developers don't know why you made a decision, they're less likely to follow it. This is true. As a matter of fact, it's so true that Neil Ford and I coined this as our second law of software architecture. I could look at a diagram and see how the architecture works. What I really want to know, and what's important, is why you chose to do it that way. Why is more important than the how. The architecture decision record is a tool, a vehicle for communication that documents that why, in both the decision part as well as the trade-offs that you made and the impacts of that decision. Let's turn the gears a little bit, talk about collaboration. Because, as most of us know in this room, software architecture is much different than software development. These activities are much different. In software architecture, a software architect identifies, first of all, what's important, those characteristics. Is it scalability? And qualifying those. Is it reliability? Is it agility? An architect has to select an architectural style. Is it going to be microservices or event-driven? And also those all-important logical components. That's what an architect does. And we complete that initial design and send it over to developers, whatever artifacts we have. And developers take that information, and what do? Well, they decide, how am I going to implement this? What class files? Maybe doing some UML, screen design, and of course, coding. You know what? This is a very traditional view of the way things work. And it is also a picture that demonstrates why it will never work. Never. And the reason is this line right here. That unidirectional handoff of all these artifacts to a development team. You see, I drew kind of a gray line between the software architecture and software development. Folks, it's not a gray line at all. You know what it is? It's actually a canyon. A huge chasm that separates these two camps. And what usually happens is all the decisions an architect is making end up right into this chasm. Developers who are really verifying our assertions and assumptions as an architect start changing the architecture, and those end up in this chasm. Yet this will never work. To get it to work, what we have to do is, first of all, fill in this gap, fill in that chasm, and form a bi-directional relationship between architects and developers, where they are on the same virtual team, working together, so that my architecture assertions, assumptions, and decisions are effectively conveyed to the development team. And as developers validate those assertions and assumptions, we work together to redesign that architecture. This, everyone, is one of the only ways I've also found to facilitate that leadership and mentoring and coaching that a software architect does. These are two camps. But in order to get software to work, software architecture has to be done with software development together to build software systems. So how do we do this? How do we do this? Well, here's the second rule I'm going to show you. If developers aren't involved in a decision, they're less likely to follow it. Do this because it performs better. Yeah, okay. But later on, we found kind of a better way to do it. Let me show you a real problem. So the architect says this. We're going to use request-reply messaging between our services because, there's the justification, because it's faster and more scalable. Actually, says the development team, we all decided to use REST because it's just as fast and scales just as much. Don't believe us? Check Google or ChatGPT. That's what it told us. But this is my decision. I'm the architect. I should be making this. Yeah, whatever. We're moving forward with REST. Hey! This is not a very healthy or collaborative environment. But did you notice what the architect did? Did the architect collaborate with the development team? No. The architect communicated. So, one of the main tips I can give you is this: DDD. But it's not domain-driven design. It's that demonstration defeats discussion. It is a very powerful tool. Let's listen to the conversation again. The architect says, I ran some benchmarks between REST and messaging in our production environment. Hey, come here, take a look at this. Look at this graph that we have now. Because here's the comparison in our environment between REST and messaging. Now, this is the load that we're expecting, and this is our planned service level agreement or objectives. And you can see down here it's fine, but once we start getting under load in our environment, it's not going to work. So, says the architect, what I'm proposing based on this is I think we should probably use messaging. What do you think? This is collaboration. Because the development team says, wow, yeah, we were thinking of using REST, but based on this, you're absolutely right. We're on board. We're going to use messaging. It's one effective way of doing that kind of collaboration. And the next tip, architecture decision records to the rescue again. Remember I talked about that status, proposed, accepted, or superseded? I like adding a fourth status, RFC, request for comment by a certain date. I make an architecture decision. Developers are busy, but I want to collaborate. What a great vehicle for having my developers be able to look at that decision, comment on it, critique it, see something wrong, say it was good, by that certain date. It's a fantastic way of getting developers involved in the architecture. Risk storming is another fantastic method of being able to ensure this alignment. But by effectively communicating and collaborating, that's really how we keep architecture aligned with implementation and make architecture work. All right. So I want to leave you with this, one last quote. This is a direct quote from Neil and I's book, The Fundamentals of Software Architecture. Developers should never take components designed by architects as the last word. Rather, those initial artifacts should be viewed by developers as an initial draft, where implementation is what reveals all the details and refinements. It is not an implementation detail, my friends. It's part of making architecture work. Awesome. Thank you so much. All right, thank you.